So at this point, we already know enough that we can actually start making proofs about complexity classes. So what we're going to do is we're going to go through an exercise where we're going to compare complexity classes actually across different models of computing to give us some sort of idea for how these complexity classes might help us to sort of explore more deeply this idea of computing and complexity. So I have this problem. I only bake NAND gates, and I ate all of my and or not gates. So if I have some sort of circuit that is defined using and or not gates, I might want to know how many NAND gates might I need in order to compute that same function. So did I bake enough NAND gates in order to implement the function that was defined using and or not gates? Now we know that any function that we can implement with and or not can also be implemented with NAND. That was a computability question. And since we said that NAND was universal, that is, it could implement any finite function, and or not was also universal, those could together implement any finite function as well, then it's certainly possible to find an AND circuit. But we still have the complexity question of whether or not we have enough NAND gates made in order to implement that chosen circuit. So what we're going to show is we're going to show that any circuit that could be implemented with S and or not gates, we're going to be able to implement with 3S, or no more than 3S NAND gates. Before we get started with our proof, we're going to need to introduce just a little bit more notation. So we said that size of S was going to represent the set of all functions that can be implemented using S or fewer NAND gates. We're going to say that size superscript AON of S, that's sort of changing our computing model. So size AON of S is going to represent the set of all functions that can be computed using at most S and or not gates. So the same idea as size, but instead of counting NAND gates, we're counting collectively the number of and or not gates. So now we have everything we need in order to show our theorem. So what we're trying to show is we're trying to show that the set of all functions that can be implemented using S or fewer and or not gates is a subset of the set of all functions that can be implemented using 3S or fewer NAND gates. So let's show how it is that we know that size AON of S is a subset of size 3S. So to do this, what we're going to do is we're going to consider some arbitrary AON circuit. So let's start with our AON circuit, and that circuit is going to have S gates in it. So we're going to have some arbitrary AON circuit that uses S gates. Next, what we can do is we can take any gate in that circuit and consider it as syntactic sugar for a NAND circuit. So now when we consider this and or not gate as syntactic sugar in a NAND circuit, what we can do is think about how many NAND gates are we going to need to sort of eliminate that sugar so that we only have NAND gates. So to answer this question, what we can do is we can look at our rules for how we could logically construct each of the and, or, and not gates using just NAND gates. So we can see that a not gate can be made by taking some input A and making it both inputs to NAND so that the output was going to be the opposite of A. We could do and by taking A with B and putting those as the inputs to a NAND gate. So now we get A NAND B out of there. And then, since NAND of A and B is the opposite of the AND of A and B, we can put that result as both of the inputs into a NAND gate, and now we have A and B as the result of that. And then, what we can do, if we wanted to build OR, is we could take A and give that as both inputs to NAND, so we have not A as a result of that, and now we have B, give that as both of the inputs to an AND, and now we have not B, and then we can do NAND on not A and not B, which if we applied De Morgan's law to that, that is equivalent to A or B. So now what we can see is that no matter what gate we had in our AND or NOT circuit, we were going to be able to take that gate and convert it into NAND gates only using, in the worst case, 3 gates. So NOT uses 1, AND uses 2, or uses 3. So certainly it's safe to conclude that any AND or NOT gate that we started, any of those S AND or NOT gates that we started with, we were going to be able to convert that into just NAND gates using no more than 3 gates each. So now when we're trying to undo the sugar from the AND or NOT gate to convert that into a NAND circuit, what we can do is we can say, to undo the sugar for each of the SAON gates, we will produce no more than 3 NAND gates. So that means that in the worst case, an S-gate AON circuit requires no more than 3S NAND gates. In other words, for any function where S and or NOT gates was sufficient to implement that function, we're going to be able to conclude that 3S NAND gates was also going to be sufficient for implementing that same function. So every function that belongs to size AON of S is also going to belong to size of 3S. Now, something to be careful of. What we have shown is that any function that's implemented, that we can implement using S or fewer and or NOT gates, can be implemented using 3S or fewer NAND gates through this kind of translation of and or NOT gates into NAND gates. That might not, though, be the most efficient way to do that. So we could end up with some sort of circuit for that function that is larger than the most efficient circuit. And that is okay. Because even though we ended up with something that was larger, since this 3S was an upper bound, every function that could be implemented with fewer than 3S gates also belonged to size 3S. All right, now it's your turn. Here we're trying to prove something similar to what we just showed, but we're kind of going in the opposite direction. So what's the upper bound on our NAND circuit size that is still going to allow us to conclude that any function that can be computed with a NAND circuit of a certain size could also be computed with an AND or NOT circuit of a certain size. So basically fill in the question mark that's going to cause this statement to be true, and then justify your choice of that question mark. So a question mark, a value for the question mark that I found that would work was going to be the floor of S over 2. Basically the idea here being that we could take any NAND gate and convert it into 2 gates, an AND gate followed by a NOT gate. So that means that any circuit that I had, any NAND circuit that I had that used S over 2 gates, I could convert that into an AND or NOT circuit with S gates by just replacing every one NAND gate with 2 AND or NOT gates. So now, as a final exercise for you, just to make sure that you can check your understanding about how we can actually use these complexity classes in order to make some pretty big statements. Here I've brought in the last 2 theorems together, so we know that size of S over 2 is a subset of size AON of S, which is a subset of size of 3S. So see if you can convince yourself that these 2 containment properties allow us to conclude that an optimal and or NOT circuit for some function f, and here by optimal we mean the circuit which requires the fewest gates. So if we have the circuit, an and or NOT circuit for f that requires the fewest gates, and we naively convert that into a NAND circuit just by using the syntactic sugar method, we can actually conclude that that resulting circuit is not going to be any more than 6 times the size of the optimal NAND circuit for f. So see if you can convince yourself that is true. If you're struggling to see why, then please show up to office hours, or you can ask questions in the week 5 chat. So notice that by looking at these theorems that we've shown so far, changing among the models of computing is actually just going to differ the amount of gates that we have by some constant. We're at worst double if we go from NAND to AND or not, and we're at worst triple if we go from AND or not to NAND. So in order to transfer functions among these models of computing, I'm actually only going to end up with constant differences in the number of gates that are going to be required. So because we have only these constant changes, if we don't want to think too hard about the model of computing that we're using, we could just sort of ignore the constants. That way, if we have some function and we say that that function requires s squared gates, it doesn't matter if I'm talking about and or not gates or NAND gates, because since the difference is only going to be a constant, it's still going to be roughly s squared gates regardless of the type of gates I'm talking about. So this is why, as computer scientists, we oftentimes will just totally ignore the constants. We'll just look at something and say, the constants don't matter. And that's because it just ends up being this pretty general rule that when you're transferring among similar models of computing, the difference in the resources that are going to be required are only going to be a constant. So if we don't want to have to pay super close attention to which of several very similar models of computing that we're talking about, then we can just ignore the constants, and then that becomes a non-issue.